Section 250.6 of the National Electrical Code, NEC, specifically addresses the prohibition of connecting grounding electrodes to the grounded conductor of a supply system. In the described scenario, where a three-phase pad-mounted transformer, primary rated at 13,200 volts and secondary at 480W/277 volts, and the panel it serves are both grounded to the same 4/0 copper conductor, a violation of 250.6 occurs. The grounding of both the transformer and the panel to a single grounding electrode, in this case, the 4/0 copper conductor installed in the pad, establishes a parallel path for the grounded conductor. This parallel path creates a situation where a portion of the neutral current can flow through the grounding system instead of solely through the intended neutral conductor. This can lead to several potential problems. Firstly, excessive current can circulate through the grounding conductor. During normal operation, the grounded conductor, or neutral, carries the unbalanced load current back to the source. However, when a parallel path is introduced through the grounding system, some of this current will divide and flow through the grounding electrode conductor. This can result in an overload of the grounding conductor, potentially causing it to overheat and fail. Secondly, the presence of current in the grounding conductor can introduce noise into sensitive electronic equipment. The flow of current in the grounding system creates electromagnetic fields that can interfere with the operation of electronic devices. This can manifest as data corruption, communication errors, or erratic behavior of equipment. Thirdly, ground loops can be created. A ground loop occurs when there are multiple ground paths between two or more pieces of equipment. These loops can introduce unwanted current into the grounding system, further exacerbating the problems associated with parallel ground paths. The NEC mandates that grounding electrode shall not be connected to the grounded conductor of a supply system to prevent these problems and ensure a safe and reliable electrical system. To rectify this violation, it is essential to provide the panel with a separate grounding electrode system. This can be accomplished through several methods. Firstly, installing a dedicated ground rod. A ground rod is a metal rod, typically made of copper or copper-clad steel, that is driven into the earth to provide a low-impedance path to ground. The NEC specifies the minimum size and depth requirements for ground rods, which are typically found in Article 250. Ground rods should be installed at least 8 feet into the earth and should be a minimum of 5/8 inch in diameter. The ground rod should be connected to the panel's grounding bus by using a grounding electrode conductor of appropriate size as determined by NEC Table 250.66. Secondly, connecting to a cold water pipe. Metal underground water pipes can serve as effective grounding electrodes, provided that certain conditions are met. The water pipe must be in direct contact with the earth for at least 10 feet. It is also essential to ensure that the water pipe is electrically continuous and that there are no insulating couplings or sections that would interrupt the ground path. A connection to the water pipe should be made within 5 feet of its point of entry into the building. Thirdly, utilizing other approved grounding electrodes. The NEC recognizes other types of grounding electrodes, such as ground rings, concrete-encased electrodes, and other locally available electrodes. Ground rings are continuous conductors that encircle a building and are buried in the earth. Concrete-encased electrodes, also known as grounds, consist of a steel reinforcing bar encased in concrete that is in direct contact with the earth. The selection of the appropriate grounding electrode depends on site conditions, soil resistivity, and local requirements. Regardless of the type of grounding electrode selected, it is crucial to ensure that the grounding system is properly installed and maintained. All connections should be made using approved connectors and methods, and the grounding system should be inspected periodically to verify its integrity. It is also important to consult with a qualified electrical contractor or engineer to ensure that the grounding system meets all applicable codes and standards. By providing a separate grounding electrode for the panel, the parallel path for the grounded conductor is eliminated. This helps to ensure that the neutral current flows only through the intended neutral conductor, preventing overloading of the grounding conductor, reducing noise in the grounding system, and eliminating ground loops. Furthermore, this ensures compliance with NEC 250.6, promoting a safer and more reliable electrical system. In summary, grounding both the transformer and the panel to the same grounding electrode creates a parallel path for the grounded conductor, violating NEC 250.6. To correct this, a panel must be provided with a separate grounding electrode, such as a ground rod, connection to a cold water pipe, or other approved grounding electrode. This ensures a safe and reliable electrical system by preventing excessive current in the grounding conductor, reducing noise, and eliminating ground loops. The NEC is very specific about grounding and bonding requirements for electrical systems. The purpose of grounding and bonding is to create a low impedance path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault quickly. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting all non-current carrying metal parts of the electrical system together to create an electrically continuous path. The NEC provides detailed requirements for grounding and bonding in Article 250. This article covers everything from the types of grounding electrodes that are permitted to the size of the grounding and bonding conductors that are required. It is essential to follow the NEC requirements for grounding and bonding to ensure a safe and reliable electrical system. Failure to properly ground and bond an electrical system can result in electrical shock hazards, fire hazards, and equipment damage. The situation described highlights the importance of understanding and adhering to the NEC requirements for grounding and bonding. By grounding both the transformer and the panel to the same grounding electrode, a parallel path is created for the grounded conductor. This can result in excessive current flowing through the grounding conductor, which can create a fire hazard. In addition, the parallel path can interfere with the operation of overcurrent protective devices, which can prevent them from clearing a fault quickly. To avoid these problems, it is essential to provide the panel with a separate grounding electrode. This will ensure that the grounded conductor only carries the unbalanced load current and that the grounding conductor only carries fault current. In addition to providing a separate grounding electrode for the panel, it is also important to ensure that the grounding and bonding conductors are properly sized. The size of the grounding and bonding conductors is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of grounding and bonding conductors that are required for different size service entrance conductors. It is important to use the correct size grounding and bonding conductors to ensure that they can safely carry the fault current. Another important aspect of grounding and bonding is to ensure that all connections are made properly. All connections should be made using approved connectors and methods. The connections should be clean and tight to ensure a low impedance path for fault current. Improperly made connections can create a high impedance path, which can impede the flow of fault current and prevent overcurrent protective devices from operating properly. In summary, grounding and bonding are essential for electrical safety. It is important to understand and adhere to the NEC requirements for grounding and bonding to ensure a safe and reliable electrical system. By providing a separate grounding electrode for the panel, properly sizing the grounding and bonding conductors, and making all connections properly, you can help to prevent electrical shock hazards, fire hazards, and equipment damage. When dealing with electrical installations, it is always recommended to consult with a qualified electrical contractor or engineer. These professionals have the knowledge and experience to ensure that the electrical system is installed in accordance with all applicable codes and standards. They can also help to identify potential hazards and recommend solutions to mitigate those hazards. The NEC is a complex document, and it can be difficult to understand all of the requirements. A qualified electrical contractor or engineer can help to navigate the NEC and ensure that your electrical system is safe and compliant. Furthermore, local jurisdictions may have additional requirements that are not covered in the NEC. A qualified electrical contractor or engineer will be familiar with these local requirements and can ensure that your electrical system meets all applicable codes and standards. In the specific scenario described, the qualified professional can assess the site conditions, soil resistivity, and local requirements to determine the most appropriate type of grounding electrode for the panel. They can also ensure that the grounding and bonding conductors are properly sized and that all connections are made correctly. Ultimately, the goal is to create a safe and reliable electrical system that protects people and property from electrical hazards. Ignoring these code requirements introduces significant risk. The amount of current returning on the ground can create a shock hazard and damage sensitive equipment. A ground fault can occur when there is an unintentional electrical path between a source of current and ground. This can happen if a wire becomes loose and touches a metal enclosure, or if insulation on a wire wears away and exposes the conductor. If a person comes into contact with a ground fault, they can receive an electrical shock. The severity of the shock will depend on the amount of current flowing through the person's body. Even a small amount of current can be dangerous, and a large amount of current can be fatal. Properly installed grounding and bonding systems help to reduce the risk of electrical shock by providing a low impedance path for fault current to return to the source. This allows overcurrent protective devices to operate and clear the fault quickly, minimizing the amount of time that a person is exposed to the fault current. In addition to protecting people from electrical shock, grounding and bonding also help to protect equipment from damage. Ground faults can cause equipment to overheat and fail. By providing a low impedance path for fault current to return to the source, grounding and bonding help to prevent equipment damage. In some cases, a ground fault can cause a fire. If the fault current is high enough, it can ignite flammable materials. Grounding and bonding help to reduce the risk of fire by providing a low impedance path for fault current to return to the source. This allows overcurrent protective devices to operate and clear the fault quickly, minimizing the amount of time that the flammable materials are exposed to the fault current. Therefore, the cost of correcting the grounding issue is minimal compared to potential damage, injuries, or death.